in today's lecture I am going to continue our discussion on Hamilton-Jacobi equation, which we started in the last lecture, and I am going to talk about specifically how to solve the Hamilton-Jacobi equation for a special class of Hamiltonian problems. Okay. So, before I do that, I want to continue our discussion. So, let us recall what is our Hamilton-Jacobi equation. This is an equation through which we were able to solve for the generating function, which leads us to the symplectic map between one Hamiltonian system to the other. So, recall the Hamilton-Jacobi equation was of the form del phi del t plus h of t comma q bar comma del phi del q1 to del phi del q n, okay, set equal to 0, where my phi is my generating function, which gives us the symplectic map we are after, and h is our Hamiltonian in the original frame of reference, that is t comma q bar. Okay. So, let us continue this discussion on the solution to this equation. I have an example to begin with. So, the example that I have is, I am going to continue our numbering of the example starting from our previous lecture. So, this is example 6. So, the example that I am going to discuss is that of simple harmonic oscillators. Okay. So, in this case, the Lagrangian for the simple harmonic oscillator is as follows: L t comma phi dot. This is also equal to m L square phi dot square by 2 minus m g L 1 minus cos phi. Okay. So, the moment we have, so where this is the contribution from the kinetic energy, and this part of this function is the contribution from the, so this is my kinetic energy and this is my potential energy of the system. So, note now the next stage of solving the Hamilton-Jacobi is to write the conjugate variables. To determine the conjugate variables, we have P, which is del L del phi dot. This is a problem with one variable, one dependent variable phi. So, del L del phi dot, the only phi dot appearing is in kinetic energy, will give us to be m L square phi dot, right, and my Hamiltonian is the sum of the kinetic plus the potential energy. So, my h of t comma phi comma p is m L square L square phi dot square by 2 plus, so sum of kinetic plus potential energy 1 minus cos phi. Now, notice that we have the variable p instead of phi dot. So, I am going to replace phi dot from the expression above. Phi dot is p divided by m L square. From here I get the expression that h is p square by 2 m L square plus m g L 1 minus cos phi. Okay. So, then what we have is, so my Hamilton-Jacobi equation, from here it is quite easy to find. This will be equal to, now I am going to write down the equation in terms of capital phi. Note that this phi in the argument of the Hamiltonian is the angle, and this phi here is not to be confused with the phi here. This phi is our generating function. So, students should not confuse between the two phi's. So hence this is written in a slightly different notation. So del phi del t plus the Hamiltonian, now in the Hamiltonian I am going to replace p by del phi del phi del phi. So this, the phi in the numerator is the generating function and the phi in the denominator is the angle phi. So now I have the Hamiltonian as follows. So I have 1 by 2 ml square times del phi square plus mgl 1 minus cos phi, this is also equal to 0. Okay, so then so we see so the next step involves the solution to this first order differential equation. Note, so two observations because before we find out the solution. First of all, as seen in the previous lecture, the Hj equation is a first order differential equation, right. So it's a nonlinear differential equation, and later on we will see that this equation is easier to solve. It's easier to solve provided we are able to separate out the variables, provided variables are separated, right. And we are going to talk a lot about this topic later, how to separate the variables and solve the Hamilton-Jacobi equation. Right now I am going to directly give my answer to the Hamilton-Jacobi equation in this example. Students should check that the answer here is phi of t bar comma q comma alpha, where alpha is our alpha has been, we have replaced the capital Q coordinate in the generalized momenta framework by alpha, which is a constant. It comes out to be, well, I guess well, how about we well, let's go back a slide. So we have this equation that we want to solve, and at this stage I am going to leave, at this stage I am going to revisit this problem in a few minutes, and at this point I am going to say that we will look at how to solve later for this problem. Instead, let me look at another example and we continue this discussion, arriving at a point where we have to solve for the Hamilton-Jacobi equation. So we will solve this a little bit later. Okay. So let us continue our discussion with another example. The example that I am revisiting the examples that I introduced in my previous lecture. So this is on the case of geometric optics, right. So recall, I am not going to write down the functional etc., but recall that the Hamilton-Jacobi equation in this case was the so called econal equation which we introduced. This was del phi del q1. So this is in 2D. So del phi del q1 plus del phi del, well, this was square, plus del phi del q2 square plus del phi del q3. My q3 was the independent variable t that we described earlier. So square is equal to n square, where n is the refractive index. Okay. So this example was again introduced in my previous lecture, and I introduced that this equation is the so called econal equation of geometric optics. Okay. So first of all, from physical considerations, we have that the right hand side, the refractive index is always greater than equal to 1. 1 corresponds to the refractive index of vacuum or air, of vacuum. So, that is the base index. So, we assume that my refractive index n is greater than equal to 1. This is purely due to physical consideration. Okay. And further we assume a particular form of the refractive index, so that we are able to solve this equation. Assume a particular form of n. We assume that n is of the form mu times square root q1, where mu is a constant and taken to be greater than equal to 1. Now, further, since n is greater than equal to 1, we assume also that q1, my first variable, the first coordinate q1 is also greater than equal to 1. Okay. So, that is again coming from the physical constraint here. So, well, for this problem I do have the solution. Again, I am not going to show how to solve the problem, because I have devoted the solution to the Hamilton-Jacobi equation in the later half of this lecture as well as the next lecture. So, I am going to write down the solution to this example. The solution is t phi of t comma q bar comma alpha is 2 by 3 mu square times 2 times mu square q1 minus alpha 1 square plus alpha 2 square 3 by 2 plus q2 alpha 1 plus alpha 2 t. Now, all what can be done is, students should check that this indeed satisfies my equation. So, this is indeed a solution to this equation. So, please verify this. So, please verify that this is indeed the case. Okay. Now, what we can do is, we can check certain properties of this function. Namely, first of all, we can check whether the solution is complete or not. Namely, we have to construct a determinant and construct the matrix or the Hessian matrix and find the determinant of this matrix, whether that determinant is non-zero or not. Okay. So, what I want to do is, we want to check completeness I find out the matrix M, which is my Hessian matrix, del 2 phi del q I del alpha j. So, there are two sets of vectors. One is the coordinate variable, the other is the set of unknown constant parameters, right. And this is a 2D problem. So, this is a 2D problem. I expect the matrix to be 2 cross 2. So, all I have to do is find these Hessians. I have the direct answers. I will write the answer directly, because all I have to do is substitute phi and take the necessary derivatives. The answer is as follows. I get the answer as negative alpha 1 by a, alpha 2 by a, and 0 1, and where my a is the following expression. This is mu square q1 minus alpha 1 square plus alpha 2 square. Okay. Where where my determinant, you can see that the determinant of M is well, we have 1 here and 0 here. So, the determinant of M here is alpha 2 by a. So, this is non-zero if my constant alpha 2 is non-zero and the square root of a is well defined, right. So, we are talking about real valued solutions. So, the square root should be well defined. So, once that is satisfied, once we put these two sets of constraint, we can directly find out our extremal solutions q1 and q2 from this generating function phi. So it implies that my Hamiltonian solution or the extremal Hamiltonian solution is given by beta k, where beta k's are constants, is equal to negative del phi del alpha k, right. This is from our result discussed in the previous lecture. So from here I get that beta 1 is negative del phi del alpha 1, and I have an answer for this right away. So all these answers should be checked by the students by taking all these derivatives. So it turns out to be alpha 1 a by mu square minus q2, and beta 2 is minus del phi del alpha 2. This is also equal to alpha 2 a by mu square minus t. Okay, I see that from here I invert this relation to find q1 and q2, and I see that q1 turns out to be, so q1 now is a function of t comma alpha comma beta, both are vector constants. This comes out to be mu by alpha 2 whole square times beta 2 plus t. Again, the purpose for giving the solution is that students should verify that these indeed are the solution to our Hamiltonian system, or the extremal solution to our Hamiltonian system. And q1 q2 of t comma alpha bar comma beta is alpha 1 by alpha 2 t plus beta 2 minus beta 1. Okay. So at this point I have just shown some examples as to how to come to a point where we have the Hamilton-Jacobi equation, and further for certain cases how can we solve. Well, we haven't shown how can we solve, but once we have the solution to the Hamilton-Jacobi, how can we derive the extremal to the Hamiltonian system. So the next set of discussions will involve how to solve the Hamilton-Jacobi equation. Namely, we are going to see the solution of the Hamilton-Jacobi equation for a specific class of Hamiltonian system known as the conservative functions or conservative systems. Okay, so let us see what do we mean by conservative systems. Okay, so this is a special case of or special class in which the Hamiltonian satisfies certain properties. Okay. So when I have the Hamiltonian which does not depend on the independent variable, when the Hamiltonian does not depend on t explicitly, when the Hamiltonian does not depend on t explicitly, we see that we have arrived at the conservative system. Now we have certainly seen few examples in this category, namely the cases which involved Beltrami identity, which in which the integrand did not contain the independent variable x. So that was one case. In this class it turns out that the moment h does not depend on the independent variable, it is easy to show that h, so the Hamiltonian is described by h. So h is constant along any extremal, it is constant along any extremal, right. Okay. So we will now see the solution to this class of Hamiltonian system. Now let us write the Hamilton-Jacobi equation. So in Hj equation, so the variable t can now be separated. The variable t can be separated from the generating function phi hat, right. So, which means that if we are given the Hamilton-Jacobi equation del phi del t plus, now h is a function purely of q bar comma p bar given equal to 0. See that in this equation the only function of t will appear here in del phi del t, right. So, we can always from here we can say that del phi del t is equal to minus h of q bar comma p, and let us say that they can only be equal where one of them is independent of t, the other may or may not contain t. They can only be equal when they are both a constant. Let me call this a constant f of alpha, right. If that is the case, I know that phi of t comma q can be directly integrated to show that this is negative f of alpha times t plus some constant psi which is q bar comma alpha, right. So, we can see the solution to our Hamilton-Jacobi equation in this class of problem is such that the variable t can be separated out, right. Okay. So, we have solved for this relation. Now, also notice this relation. So, the second relation implies that h of q comma p is f of alpha, right. So, the Hamiltonian is constant along the extremal q bar, where q bar is the extremal, right. So, this is constant along the extremal q bar of t comma alpha comma beta, okay. And then further we can, in our generalized coordinate, further we can simplify by identifying one of the coordinates with this constant. So, this constant is special because this will help us to reduce our Hamilton-Jacobi equation. So, what I said is the following: further simplify, we can further simplify in generalized coordinates, in the coordinates capital Q, in generalized coordinates, right, by identifying one coordinates, by identifying one coordinate q n to be equal to alpha n, which is f of alpha. So, we identify one of the coordinate to be f of alpha, the constant itself, right. So, let us now look at so what do we have here? We see that so now I want to write so in this particular case we have a special form of Hamilton-Jacobi equation, namely the reduced form, right. So, the reduced Hamilton-Jacobi equation, where my Hamiltonian does not depend on the independent variable, is the following: h of q bar comma p is equal to h of, let me write it down, q1 comma q2 comma qn comma p1 comma p2 comma pn. These are all the generalized vectors. Well, these are all the vectors in the original frame of reference. This is also equal to f of alpha, or in terms of the new coordinate, this is alpha of n, right. We have just introduced that, right. So, alpha of n is f of alpha, okay. Now, further I have been saying that wherever we get momentum, the momentum variables, we always replace this by del phi del q, right. So, we replace pi by del phi del qi, because that is the relation for the generating function in terms of the conjugate variables. Note that, so what is my phi? my phi is the solution to the original Hamilton-Jacobi equation, and we saw that phi was equal to psi of q bar comma alpha minus f alpha of t, right. We also saw that, so which means that del phi del q I will be del psi del q I, because the q variable only appears in this function psi. So, this means that we have to replace pi's by del psi del qi. Okay. So, my reduced Hamilton-Jacobi equation now reads as follows. I have that h of q bar comma del psi del q1 to del psi del q n is equal to alpha n. So, for this the solution is the function psi of q bar comma alpha, right. So, the solution to the reduced Hamilton-Jacobi equation is psi. Note that the function psi which is appearing in the original, so psi is also the function which appears in the original solution to the original Hamilton-Jacobi equation, but it is the solution, this function psi is the solution to the reduced Hamilton-Jacobi, right. So, what is it? What is the relation between the original Hamilton-Jacobi and reduced Hamilton-Jacobi? It turns out that the function psi which appears in the original, mind us that psi is not the solution to the original Hamilton-Jacobi, it only appears there. So, but it is the solution to the reduced Hamilton-Jacobi or the Hamilton-Jacobi corresponding to the conservative system. Okay. Okay. So, then some of the other issues to talk about is how about the completeness of this solution, right. So, it turns out that the solution psi to the reduced Hamilton-Jacobi equation, is complete provided m which is given by del 2 psi del qi del alpha j is non-singular, right. The same idea that we had shown for the general class of Hamilton solution to the general class of Hamilton-Jacobi equation. Okay. So, it turns out that for this reduced case it is psi that we are after. So, psi is our generating function. So, this is our generating function to the reduced Hamilton-Jacobi, and so psi produces the required symplectic map, which is S from the original coordinate q bar comma p bar to the new coordinate capital Q bar comma capital P bar, right, which transforms the Hamiltonian, h of q bar comma p bar to h hat of q bar comma p bar, right. Okay, which we have said that this is equal to our generalized coordinate qn, right. Okay. So, which means the following. From here we can see what is my Hamilton's equation. So, in generalized coordinate, when I say generalized coordinate, I talk about coordinates which are capital Q, capital P, right. My Hamilton's equation will provide the following set of constraints. I see that the first set of Hamilton's equation is qk dot is del h hat del alpha k, well del h hat del pk, and note that qk dot will be 0 for all k except k equal to n, right. Well, not qk dot but pk dot, sorry. So, let me just write down the two sets of equations and then we can infer our conclusions. So, qk dot is this and pk dot is minus del h hat del qk, right. So, notice that since h hat is not a function of p, so this will be 0, and but h hat is definitely a function of qn. So, this is 0 if my k is from 1 to n minus 1 and it is 1, it is, well, I see that this is 1 with a minus sign. So, minus 1 if k is equal to n. So, from here I can derive the fact that my qk's are alpha k, so constants. So, these are my constants and my pk is beta k. If k is beta k is another set of constants from 1 to n minus 1, and otherwise it is also equal to beta n minus t for k is equal to n, right. So, for k 1 to n minus 1 I get the constants, otherwise it is beta n minus t for k equal to n. Okay. So, we are ready to look at examples in this class of systems, in this system of in this Hamiltonian system of conservative functions. So before I do that, let me just summarize the solution strategy or how to find the solution for this class of problems. Okay. So, solution strategy for finding extrema of the Hamiltonian system, right. We start with solution of reduced Hamilton-Jacobi equation. We start with the solution of the reduced Hamilton-Jacobi equation, right, and then the generating function. Once we have the solution to the reduced Hamilton-Jacobi, which is psi, the generating function of the original Hamilton-Jacobi equation is phi, which is psi minus alpha n t, right. And finally, once we have the original generating function, we can derive the extremals from our relations as follows. So, the extremal q bar is obtained by solving the following set of equations, that beta k is minus del psi del alpha k, where k is from 1 to n minus 1, and my solution beta n is minus del psi del alpha n plus t, right, the nth component. Okay. So, from here I can get my extremal. So, let us look at some examples for this conservative system.